This is the third problem that we have in our set for circular motion. So we had a conic pendulum problem where we used the flying pig or the bat that hangs and it goes in a circle, but it's attached to a string into the ceiling. You could think of it as a tether ball. If you ever played tether ball before, the swings that you might ride at an amusement park or at a fair in the summer where you're sitting down the swings, and then it starts spinning and you start swinging outward and going around the circle that way. Those are the conic pendulum problems. The second problem we did was a banked curve problem. So when you get onto an on-ramp onto an interstate, and maybe it does the clover leaf where it turns and the road is banked at an angle so that you can get up to speed to get onto the interstate. Now, this third one is really similar to that one, other than the fact that you are not banked anymore. So this would be like you are at a corner at a stoplight and you want to go to the right, or maybe this isn't a stoplight. You are the light is green and you want to know how fast can I go around this corner. So your car is sitting on a flat surface, and what in this case is keeping your car from sliding off of the road at a straight line at a constant speed. So you picture if this were really icy, then your car would just slide off the road instead of going around that curve. So the hint there was if the road was icy, what's keeping your car onto the road there is what we would call the force of friction. So it's the friction between the tires and the road. So if I'm to draw a force diagram, then I would have a force diagram of my car where I have the force of gravity of the car is going downward. I have the normal forces going upward. And then if you picture the force of friction would be going sideways, it's what's keeping your car on the road. And that is the direction that is toward the center of the circle, towards center of circle. Notice that that force diagram looks very similar to what we did with the conic pendulum and with the banked curve problem. So in this case, we want to find out then part B, what's the force of friction? Remember that our equation for that is mu force normal. If the car isn't floating off the ground or sinking into the ground, then don't those two forces have to be equal, the normal force and the weight? So this would be mu force of gravity. And then how do we calculate the force of gravity? We calculate that by doing mass times gravity. So those are all simplified now. I can plug in some numbers. This is going to be mu 0.61 times the mass 950 times the acceleration of gravity 9.8, and I would have that the force of friction on the car is 5,679 newtons. Second, I want to find out what the acceleration towards the center of the circle is. Since I have the force pulling it towards the center, then I can say the centripetal force equals the mass times the centripetal acceleration. I already know that force of friction, and instead of plugging this number in, you can do that. I want to plug in the variables here, equals MAC. That force of friction we ultimately determined was mu mass gravity. And if you notice in this particular case, our masses will cancel out in this and all of the cases like this. And we end up that centripetal acceleration is really only dependent on the coefficient of friction, which is the two surfaces in contact, the road and the tires. So if the road is icy or wet or dry, that totally affects the speed that you can go around the corner or the velocity. And then we would times that by gravity, which is 9.8. So I can take this and do 0.61 times 9.8 and end up with an acceleration of 5.98 meters per second squared. You would get the exact same value if you put this 5679 in the left side and then divided the left side, that 5679 by 950. You also get that 5.98 meters per second squared. Lastly, to find the velocity, how fast can we go around that curve? Then we can take this and say, well, isn't that acceleration equal to v squared over r? And so if I want to find the velocity, I would say the velocity is the square root of a times r, which is going to be 5.98 times the radius of the curve, which is given to us as 13 meters, and then square root it. And we would get that our maximum velocity we could go around that is 8.82 meters per second squared. So again, notice how similar this is to the other two problems that we've done. We have our force diagram where the up and down forces are canceling out, and then there's a force that's pulling it towards the center of the circle. And from there, we play out the dynamics to find out the net force pulling towards the center of the circle, find out the acceleration towards the center of the circle, and find out what the maximum speed or maximum velocity is that we can go around the curve without sliding off of the curve. So that is a friction problem.